So as an exercise, show that the collection script B sub E, consisting of the basis elements for the even integers, is an open cover, but is not a basis for the digital line. Okay. So next, we will show that every singleton containing an odd integer is open but not closed. So proof, let M be an odd integer and let the collection script B sub E be those basis elements for the even integers. And clearly, the singleton containing the odd integer M is open, as it is a basic open set. Now notice that the set of all odd integers, or rather the set of all integers less than or equal to the odd integer M minus 2 is open, since this set is the union for n less than m of the elements B sub n, where B sub n is in the collection script B sub E. Similarly, the set of all integers greater than or equal to the odd integer m plus 2 is open, since this set is the union for n greater than m of the elements B sub n, where B sub n is in the collection script B sub E. And so the complement of the 3-point set m minus 1, m, and m plus 1 is the union of two open sets, and is therefore open. Further, it is the largest open set not containing the odd integer m, since every open set containing the even integer m minus 1 must contain the basis element B sub m minus 1, which is a 3-point set, m minus 2, m minus 1, m, which contains m, and every open set containing the even integer m plus 1 must contain the basis element v sub m plus 1, which also contains the integer m. And so the 3-point set m minus 1, m plus 1 is the smallest closed set containing the odd integer m, and so has as a subset the singleton containing that odd integer m. And so the closure of the singleton containing the odd integer m is the 3-point set containing the even integer m minus 1, the odd integer m, and the even integer m plus 1. And hence the singleton containing the odd integer is not closed, since it does not equal its closure. Further, the boundary of the singleton containing the odd integer is the closure of the singleton set minus the interior, which is the 3-point set m minus 1, m and m plus 1 set minus the singleton containing m, which is the 2-point set m minus 1, m plus 1. So notice that the boundary for a singleton containing an odd integer is the set containing the consecutive even integers centered on the odd integer m. So since it is not true that every singleton set is closed, the digital line is not T1 or Fréchet, and hence it is also not T2 or Hausdorff. So as an exercise, show that the digital line is T0 or Kolmogorov. Okay, so next we will show that the set containing the odd integers and the even integers, or consisting of the sets of odd integers and even integers, is a partition, but not a separation of the digital line Further, the set of even integers is the boundary of both sets. So proof. Clearly, the set of odd integers and the set of even integers are non-empty subsets of the entire set of integers such that the intersection of these sets is empty and the union of these sets is the entire set, and hence the set containing the set of odd integers together with the set containing the even integers is a partition of the integers. However, it is not a separation since the set of even integers is not open. Now the boundary of the odd integers is the closure of the odd integers set minus the interior, which is the entire set, set minus the set of odd integers, which is the set of even integers. And the boundary of the set of even integers is the closure of that set, set minus the interior of that set, which is the set of even integers, set minus the empty set, which is the set of even integers. And so, once again, the set of even integers is the boundary for both itself and the set of all odd integers. So now we're going to look at the digital line, and we're going to look at the basis elements, the basic open sets, in a graphical way. Now every odd integer is a basic open set, and so using a circle I will indicate that these are basis elements. Now every 3-point set containing an even integer is also a basis, and so I'll indicate that this way. Notice that especially because of the basis elements for the even integers, that we will always have an overlap. And so this is a graphical way to visualize that the space is a connected space. And so next we will show that. So the digital line is connected. So proof. We'll prove it by contradiction. So suppose that the set containing U and V is a separation of the digital line. Then U and V are non-empty, open subsets of the entire set of integers such that the intersection of these sets is empty and the union of these sets is the entire set. Now, as the set of odd integers and the set of even integers or rather the set containing these two sets, is not a separation of the digital line. Neither the set U nor the set V consists entirely of odd integers. That is, there exists even integers m and n such that m is in the set U and n is in the set V. Now, as the set U is open, the basis element B sub m, which is the 3-point set, m minus 1, m, and m plus 1, is a subset of the set U, because once again, for any topology generated by a basis, a set is open if and only if for every element in the set there exists a basis element containing it, and for an even integer, the only basis element containing it is the 3-point set. So notice that the even integer m plus 2 is not in the set V, since otherwise the basis element containing it, which is the 3-point set, m plus 1, m plus 2, and m plus 3, is a subset of V, which requires that the integer m plus 1 be in the set V. This is not possible since the integer m plus 1 is in the set U, and U and V have no points in common. And so the even integer m plus 2 is in the set U, and hence the basis element B sub m plus 2 is a subset of the open set U. But then the even integer m plus 4 is not in the set V. So we can continue ad infinitum so that the set V has no even integers. This is a contradiction because the set V cannot consist entirely of odd integers, and so by contradiction there does not exist a separation of the digital line. And therefore, the digital line is connected. So as an exercise, let the interval from A to B, or rather let this interval notation represent all integers n such that n is strictly less than A and strictly less than B. And let the set script B be the set of all such sets where A and B are integers. Show that the topology generated by this collection script B is the discrete topology. On the set of integers. Okay, so we'll end here for today. Next time we will finish up with the digital line and then move on to the order topology. So I hope you have enjoyed the 8th lecture. Thanks for watching.